Greetings, mathletes. Today's lecture is on restricted domains and piecewise functions. And so um, basically the idea of a restricted domain, um, if you remember what a domain is the set of all the numbers you're allowed to plug into a function. And so if we're restricting that domain, what we're doing is we're cutting down what we're allowed to plug into a function. And so there's a notation that goes along with that. And it affects the graphs and things like that. And so we're going to be taking a look at that. Piecewise functions are very similar, and we'll see as we go along why we're learning about restricted domains first. But let's go ahead and start with an example, right? So given a function, let's say we have f of x is equal to 10 minus 2x. And usually the domain restriction follows the function, right? They'll put a comma or a semicolon between it and then write something like 0 is less than or equal to x, which is less than or equal to 4. Now, if you remember from the previous sections, this right here, this inequality, is actually the interval from 0 to 4, and it includes the endpoints. And so only the values that are inside this interval, right? Because that's actually what this inequality means. But only the values that are in this interval are allowed to be plugged into the function. Everything else is off limits, right? Which means there are no function values. It's not that they're equal to 0, they simply do not exist. So you would be given something like this and told find a few function values, f of 2, f of 6, and graph. Right? And so we want to get that graphed as well. What's convenient is a lot of the time you can use the points from evaluation to do the graphing as well, because when you're plugging in values for x, you're finding values of y. Those are all points. So let's take a look here. So to start off with, f of 0, that means we're making x 0. So whatever we're finding here, it's going to be a point with its x coordinate as 0, right? Our job is just to find what the y coordinate is. Furthermore, the fact that we're plugging in a 0 for x means we're finding the y-intercept, right? Because that's always the case. If you're plugging in 0 for x into any function, you are finding the y-intercept. So let's just see what we get. F of 0 is going to be 10 minus 2 times 0, and that's just going to be 10, right? So that means we have the point 0, 10. We have an intercept at 10 for the y-axis. Then we look at the next one, f of 2, and we should probably double check here. Let's see, 2 falls in this interval, so that's no problem. So this is 10 minus 2 times 2, and 2 times 2 is 4, so this is 10 minus 4, or 6, which means we have the point 26 here. And then looking at the last one, f of 6, well, you notice 6 doesn't fit into this interval, right? So there's nothing. There's nothing I can do. It's undefined there. Now, I do want to point out that there are certain books and certain situations where sometimes it is assumed that the function value is 0 everywhere outside of this interval, but this particular book doesn't look at that. So this basically does not exist because it's not defined there. Okay, so now we have to graph this guy. And so we can use the points we've already found. In fact, we already found the point 0, 10, which is a y-intercept. We also have the point 2, 6, which is just another point. And that's really all you need to be able to graph a line, but I want a little bit more. Now, we were told, in fact, let me just rewrite the whole function here. So it's f of x is equal to 10 minus 2x. And the domain we're given runs from 0 to 4. Okay, so that means that there's nothing outside of that interval from 0 to 4. So first of all, I'm just going to go ahead and put some tick marks here. Let's say 4 is right here, so this is the other boundary. Technically, these dotted lines are not part of the graph, They're just there to help me out. So if I could find points on either boundary, right? I already know the point 0, 10 is here, and we'll just say that's 10. So there's the point 0, 10. It'd be very nice to see what's happening at 4 on the other boundary so that I can mark my second point. And so that's what I'm going to do. I'm going to see what f of 4 is. So this is 10 minus 2 times 4, which is 10 minus 8, or 2. So that means at 4, the y value is 2. And so if that's my 2, my other point should be there. And we can actually double check this point 2, oh, yeah, the point 2, 6, right? If 2 should be halfway here. If I go up here, that's a little over halfway. That's the point 6. So you can actually use that other point as a checkpoint if you wanted to. But the bottom line is this function goes from the point 0, 10 to the point 4, 2. And it's a straight line. It is a linear function, right? There is nothing outside of that. I know in the past we have graphed things, and I have made a point of saying you need to put the arrows on the ends when you look at something like this. And it is important when the domain is not restricted, because this tells you that it goes on forever. With these, though, you have to end them at the endpoints. If you go through that, you are violating the graph, you're violating the domain. It doesn't count anymore. Okay, so that's that example. We went ahead and we found those evaluation points, and we graphed this function with a restricted domain. So again, technically, the dotted line isn't here, right? It's just that line segment sitting out there in the middle of, I guess it'd be this way, sitting out there in just floating over the x-axis. All right, next example. Now, oftentimes you have what's called a discrete domain, which means that you're only allowed to put in set values, and those are listable values. You can actually write down each and every value. So let's take a look at one of those. So let's say q of x is equal to 1 plus 2x, and this time we're told x is equal to 1, 2, 3, and 4. So this is also a restricted domain, but there are only 4 values you can plug into this domain, so we can determine the entire function. So if we want to determine all of this, what you're basically going to do is just plug in those values one at a time. So if we're going to graph this, I need q of 1, q of 2, q of 3, and q of 4. Each one of these is going to be a point, and these input values are your x values. I just need to find the y value. So q of 1 is 1 plus 2 times 1, which is 3. Q of 2 is 1 plus 2 times 2, which is 5. Q of 3 is 1 plus 2 times 3, which is 7. And Q of 4 is 1 plus 2 times 4, which is 9. So that means that these corresponding y values, oops, not 5. There we go. Go along in these points. Now, if we're going to graph this, it's just a matter of getting those points on the graph, right? So we know our y values are 1, 2, 3, and 4. And then over here on our x values, we'll make these a little closer. 3, 4, 5, 6, 7, 8, 9. Ooh, push that right to the top. Okay, so we have the point 1, 3. So there's our first point. Then we have the point 2, 5, which that would be our second point. Then we have the point 3, 7, which would be there. They should actually be more on a straight line, but this is just This is my graphing. And then the point 4, 9, which will be up here. There are no lines to connect. It is simply those 4 points. That's all you need to graph. Once you have those 4 points on there, you are done. If they gave you 5 x value points, you're done with that too, right? You put 5 points in. So when you're given a continuous domain, as in up here, right, you have a solid function. But if you're given a discrete domain, meaning it's just a list of points, all you need to do is plug in those points and plot those points exactly and nothing else. There's nothing else in the function but that. All right. So that concludes the first part of this, discussing restricted domains. In the next video, we're going to be taking a look at piecewise defined functions and going from there. So, all right, folks, keep your wits and your pencils sharp, and I'll see you next time.